Hi, I'm Kyle Fitzsimmons, and I'm a research assistant at the Trip Lab in Concordia University in Montreal. I've been focused on public transit data over the years, and we were looking to use our methodologies and experience from that for studying GPS points in relation to environmental exposure, specifically for health studies. And this was under the supervision of my professor, Dr. Zachary Patterson.
I'm Zachary Patterson. I'm an associate professor at the Concordia Institute for Information Systems Engineering and director of the Trip Lab. And we're the ones, well, Kyle works in the Trip Lab, and the project that Kyle will be presenting today on the open source library, what we call the Trip Kit, was initially instigated by Dan Rainham, who also collaborated a lot on this project.
Hi, everyone. I'm here to present the Itinerum Trip Kit, an open source library we developed at Concordia in Montreal for processing GPS travel data. So initially, why? We find increasingly geographic data is being used more and more in health research, but it's difficult to precisely measure the time of activities, travel patterns that occur, or environmental exposure. With technology as commonplace as smartphones now, we now have tools to measure with incredible precision the context of activities, such as their durations, their physical intensity, their carbon intensity, and in particular, their proximity to things like polluted zones or the duration of a participant's exposure to certain environments. The other issue is using geographic data is complicated, especially for researchers not within a GIS field. And lastly, researchers wind up developing their own methods every time, and it makes it very difficult to compare between study to study. Many disciplines face questions like this, specifically how and why trips are made, such as city planners wishing to understand demand for subways and buses. So we've tried to create a toolkit that unifies approaches between these different disciplines. Traditionally, to collect location data, we had three different approaches: time use diaries, where respondents fill out a timetable of their activities over a determined interval; a prompted recall method, which is usually done through a caddy approach. This is common with larger planning surveys where researchers are interested in modeling large patterns at a scale over a relatively compact time span. But these are costly and laborious. They're subject to recall bias, where people simply forget some of the trips they took. Or there's proxy bias, where respondents are answering for other members of the household and don't necessarily know what everyone is doing. Other approaches are a web-based tool, such as Qualtrics, which allow for more complex surveys, but there's limited resources on how to best design these. And a more complicated approach, also custom built, is a smartphone platform, but these can also be extremely costly and difficult to edit. So the third way to do things is with a passive GPS device, where respondents are asked to carry around a receiver. And this may be combined with other methods such as a paper travel diary, but this is a bulky, expensive device and another thing to keep track of. And it requires some tech ability to download and share the data. So once we have the data, the big question is, how do we use it? As the surveys grow that we're trying to do, the complexity of working with this data scales as well. First, you need expertise in databases. The data must be stored compactly, efficiently, and securely. So that requires good familiarity with the trade-offs between the different types of databases. With our Trip library, we're trying to abstract that away, so as a researcher, you don't actually have to know the nitty-gritty details. Secondly, is the geospatial expertise. Just knowing whether a latitude and longitude is appropriate, or you need to use a metered grid to be able to find to do calculations such as distances between points, and what are the trade-offs of using these different types of systems between speed and accuracy versus having a global grid. Next is data structures. Once we have the data for a GPS point, how do we represent it in a way that a computer can understand? And how do we join additional data to this to make it useful for things like measuring exposure for the entire duration of a trip? And then the last thing that someone needs domain expertise in is the building of algorithms and the processing of points. So that's what we've included here with trajectory cleaning, point clustering, and stop versus trip identification. So what is the trip kit itself? It was initially based on some core tenets from this paper GERT, which was the GIS episode reconstruction toolkit with 3 core tenets: transferability between researchers, modularity for being able to program in specific new routines, and scalability to work with large data. We've added a 4th tenet here that we call approachability, which is making it easy to work with. So in the end, TripKit is an approachable tool set for providing trip analysis on GPS data. We've written in Python, which is common and familiar to data scientists. And we've really worked to create a framework that can be easily followed between researcher to researcher. These methods are something that we've tested and tried at scale with our existing large-scale transit surveys. So far, we've got 2 platforms that we support: our existing Itinerant smartphone app, which exports CSV data, and then more commonly familiar to health practitioners is the QStar GPS receiver, which also exports CSV. Anything that exports CSV, we can work into the workflow as long as there's latitude, longitude, timestamps, and accuracies for the algorithms to process. So now we're going to get into just what the TripKit itself does. This is where we think it can save researchers a lot of time and avoid trying to recreate the wheel between studies. Beyond dealing with the various formats of GPS data, GPS itself can be far from clean. And over the years, our research has identified some of these common issues. One particular case is when, although points are pretty good at describing whether they have been an accurate measurement, sometimes an inaccurate point is located far away from the actual trajectory. We've included a test here which measures to see if the speed is realistic and can filter out these points. One of these calculations is pretty difficult to do in GIS, and that's why we feel it's necessary to have a toolkit that can process these points specifically. Additionally, we look to identify days that are incomplete because this provides us with a good measure of whether one day is comparable to the next. And lastly, we're looking to remove any excess data that exists within the data set to start with, because this is something that significantly slows down the processing as steps compound. So what is the actual reason for this is we have to work with time series data with GPS points. And this is not something that is a traditional workflow for someone who's used to dealing with an Excel spreadsheet. Although we have GPS points in a spreadsheet form, the way to extract useful information from this is through grouping. Through grouping, we'll be able to determine a trip distance, a speed, the durations between trips, such as stop times, the exposure, and eventually we can start inferring more complicated contexts, such as how trips were made by a bicycle, walking, car, or the levels of exertion along the way. Grouping is tedious. It's prone to error between different researchers because everyone has their own patterns that they identify, and it's extremely difficult to optimize. So through the introduction of a general library, we feel that many hours can be saved on programming for researchers. However, the way to process the data between our 2 different tools, a dedicated receiver and a smartphone application, are themselves different. A dedicated receiver will continually run its GPS collection in the background at all times. This means even at stops, we can collect points that are erratic and drift around due to the environmental noise of GPS. Smartphone, however, are looking to conserve their battery life. So this can lead to large skips in timestamps and gaps between GPS coordinates. It's important to note, however, that this behavior is itself not always perfect, and there sometimes can be gaps that exist for other reasons. When these gaps exist, we have to identify them and tie them back to the previous point. So I'll explain that in the next 2 slides. For the dedicated device, as mentioned, we get a continuous trace with environmental noise. What this does, however, is it gives us 2 clues when we're looking at the data that a stop might exist. It means that the speeds between point to point are highly variable, and it also means that the distance changes constantly. Using this, we can create a clustering approach that looks for this behavior and seeks to identify it. When we've identified clusters of these points changing rapidly, that for us is what identifies a stop. In the smartphone application, it's a different approach. There will be a break in the data. We look for breaks between the timestamps and eventually larger breaks between the GPS positions. Sometimes this can occur for other reasons though, such as a user going through a tunnel or the warm-up time from a user leaving their house before they receive their first signal. So more complicated behavior has to be included in the toolkit. In this case, that means that we create a proxy start point at the previous destination to account for the warm-up time. The point of these slides is really to illustrate all the different cases that a researcher must account for when they're building their own processing. This is what we're trying to build by creating a generalized toolkit so it does not have to be redone each time. The outputs here, you get a series of reports in CSV format that are easy to work with, trip summaries, the dwell times at stop locations, and a summary of the complete days. Then you can also export GIS data, so it can be used within familiar tools such as ARC or QGIS. And this converts the incoming CSV data into useful files such as shapefile. And lastly, we have the ability to tie into external services. So as a demonstration, there's an OpenStreetMap API that allows GPS points to be map matched to their real life roads. There are some pitfalls to mention. There's always difficulties with using GPS devices because you can't exactly ask the device what went wrong. They're intermediaries between users and the researchers themselves. And existing devices, services, although they may appear attractive, also have their own caveats to be aware of. In our own research at Concordia, using Google locations with a predetermined itinerary, only 51 of these locations were correctly identified by Google location, 32% of the trips. So for us, this indicates that more sophisticated tools have a spot in this research domain. However, we need these secondary tool sets to be able to use them usefully. So how do you get started yourself? We've put this available on GitHub at our TripLab domain. You can also install it through the Python package repository as you would any other Python library. Or if you're not familiar with coding itself, we've tried to provide a front-end command line interface so you can get started with that alone. You install it the same way as with pip. So thank you very much, and that concludes our presentation today.